need to do something soon, and I'll just talk to Chuck.
Did you get a nice tour?
Okay, I think we should get started. Listen, for these introductions, we like to tell stories, anecdotes. I just met Dr. Gosling just now. And I don't think he needs an introduction. I think we've all used some of his software at some point in our lives. So instead of giving him an introduction, I just want to ask him a question to make sure we're all in the right place. Do you like robots?
Well, it depends on how they're behaving.
So then I'll ask
Lately, I've been kind of cranky on the subject of robots.
So you'd say your relationship with robots is a love-hate relationship?
It's more of a love-kick relationship.
So what I'll do is, I'm going to give you this button here that you can wear to show off your love.
Actually, what I need to do is...
Well, without any introduction, we have Jim Gosling come give us a fine talk. Please ask as many questions as you can. He wants this to be as interactive as possible.
I'm James Gosling. I had the misfortune of graduating from this godforsaken institution about 30 years ago. When the School of Computer Science wasn't here, it was just like the Computer Science Department and the Robotics Institute. But it was a lot of fun, and I've sort of gone on a merry tour for quite a while. In the last few years, I've been doing robots, but kind of unusual robots. A friend of mine. There were these folks that had started this company to do marine robots, and so it's like robots in the ocean, and they need software. It's a bunch of mechanical engineers, and they really need software. So I thought, what could be more fun than robots in the ocean? So these are not your typical robot. They don't have arms and legs or wheels or anything like that. They've got a float. And they've got a piece that sort of dangles below. There's this umbilical cable, and on a good day I get to swim along with them. And this is only on very good days. And you know they're out there in the ocean, and there are actually several hundred of them out there right now, mostly doing missions for scientists of various sorts. The company got started really in like 2005. There was this guy named Joe Rizzi who was one of the early guys at Fairchild, made more money than God, ended up as a venture capitalist, nice big house on the Kona coast of Hawaii. Back lawn, goes down to the beach. Humpback whales dancing outside his window, and he's, you can see the humpback whales jumping up and down. And, as an electrical engineer, he was kind of like, well, gee, I'd like to be able to listen to them too. And he did the kind of things that an electrical engineer would do, namely, taking a microphone and a piece of wire and, rowing out and dangling, the microphone in the water and learning the 10,000 ways that hydrophones fail. And at some point he decided that what he wanted was something more like an RC car to go out and listen to whales. And so he got this guy named Roger Hine, who was a mechanical engineer specializing in robotics. Mostly what he did was designing machines to fabricate integrated circuit chips. And his dad was this guy named Derek Hine, who was an aeronautical engineer. And so together they came up with this crazy gizmo. And then in 2007, they kind of went, well, can we turn this into something that's not just an RC car for the ocean, that's something that we can actually use, because there are things that you can stick in the water that are interesting besides hydrophones, all kinds of scientific instruments. So in 2007, they decided to try to turn it into a company, yada, yada, yada. They needed software. I joined. So the bot is pretty simple. It kind of the hull is sort of a cross between a surfboard and a kayak. On top, it's got a bunch of solar cells. There's a bunch of antennas in the middle, and then down below there's this wing rack. So the wing rack is down where the water is calm, and it's being pulled up and down by the float, which is bobbing up and down on the waves. And so you get this sort of this motion of the wings, and the wings are actually held in with springs, right? So as it goes up and down, it's literally exactly like a whale's tail in terms of generating thrust. So this device generates thrust with absolutely no computer control at all. You know, it's a completely passive control system. It's literally a float, a cable, some wings, and some springs. And you know, with no control system at all, it's going. So it's got a motor that generates somewhere around 1,000 pounds of thrust. And it's the motor that never stops. It's going 24 hours a day. And up top there's a bunch of batteries, you know, a processor, antennas, and the rest of it. And there's not much on this thing that can actually be controlled, that can be actuated. So there's the float. And this is actually a diagram from an earlier model, but here's the float, the wing rack. This is sort of the old style wing rack. And then you can attach all kinds of instruments. You can attach cameras and wave sensors, and this thing here is something called an ADCP, an adaptive Doppler current profiler. It's something that sort of looks down in the water column and bounces ultrasonic signals off of all the little pieces of sand and stuff that are floating, all the particulate matter, and then it generates velocity vectors for all the little particles. It's kind of like a 3D optical mouse that gives you current vectors so you can tell what's going on in the water underneath you. Very slick little device. But we can carry around all sorts of stuff like that, and the only actuator is the rudder. That's the only thing that we can mechanically move. The new ones have a little thruster at the end. It's with an electric motor. We don't actually use the thruster very much at all. It's only for if we get into trouble. But it's a really simple control system. Most of it is quite passive. But one of the nice things about a really simple design like this is it's easy to make it very, very robust. And that's where, you know, from a mechanical engineer's point of view, a lot of the energy goes into is making this thing really robust. To communicate, we mostly use the Iridium satellite network. It's a particular sub-part of Iridium called Iridium SBD, or Iridium Short Burst Data, which is almost literally text messages. But they're not cheap. Iridium SBD is about $1 a kilobyte, and we get about 1/3 of a kilobyte a minute. So, I mean, you guys are used to, you know, gigabit per second networks, absolutely free. When your network protocol is $1 a kilobyte, you know, you think about networking differently. You think about how you encode the packets differently. You think about, you know, whether or not you should send a packet at all differently. You get really cranky about how, people work a lot to compress the data part of packets, but they kind of don't worry about the metadata parts because metadata tends to be such a small part of a packet. But when you're at this kind of scale, you know, you have to worry about everything in the network. So it's really a small number, and even with a large number of robots out there, when you're spending that much money to collect data, right? If it's $1 a kilobyte, it's $1 billion for a terabyte, right? So you go down to the nearest electronics store, you can buy a 4 terabyte drive for not very much. By the time you've filled up your first disk drive, you've spent enough money that you could have afforded to launch your own satellite network. So we deeply don't have a big data problem, at least when we're far from shore. Yeah, I mean we can take all the data we've collected and put it in RAM on my laptop, because it's $1 a kilobyte. That is, unless we're close to shore. If we're within about 15 miles of shore, then we'll use cell phones. Yep.
As long as you want interactive. So what is the pressure for real-time data? I mean, why not just have this thing every once in a while come back to shore, you pick up your 4 terabyte disk and replace it with a new one?
So it depends on what.
$30.
So it depends on what kind of data you're collecting, right? So if.
Right, so you haven't even mentioned that yet.
Right. So if we're doing like seismic data for an oil company, then yeah, we actually put terabyte drives in there, and we have like wet mateable in saltwater SATA connectors, so you can hot swap SATA drives in salt water. The connectors cost a lot more than the disk drive. But there's an awful lot of data for which you have to have it now. So like one of the things we do is collecting data for NOAA, right? So if the data is being used for weather prediction, you kind of need it now. One of the things about these guys is they're really, really robust, so they will happily go through hurricanes. So we're like the only data source from the underside of a hurricane. And people like to get it through live. So because of this, we have really different durability issues from most people's robots. We have to deal with really high seas. So we're not in like a lab, we're actually in an ocean. And oceans, when you're on like a beach vacation, they're kind of friendly. But if you're trying to be in the middle of a hurricane, you're talking 190 mile an hour winds, 60-foot waves at least. We've had some really So we had one incident. So typically in a hurricane, what you get is what's called swell. That's the sort of wave energy that accumulates over a long time, and so you get these long period waves. But there are also wind-driven waves, which are usually referred to as chop. And usually chop, if you look out on the ocean, it's the big waves are swell, and the little sort of flecks on top of the big waves are chop. If you have had a really flat sea and suddenly the wind just snaps up to 150 miles an hour, you get very large chop. So we had an incident this 5 or 6 months ago where we had 3 robots in an area that had it was like 45-foot. Sort of 15 meter waves, but they were wind waves, not swell. So the period between the waves was 6 seconds. So think of so 45. That's like a 4-story building being thrown at you every 6 seconds, and that's. You've got to be mechanically robust in order to survive something like that. We don't know what the highest speed wind we've been in. From satellite data, we believe it's around 195 knots. One of the problems that we have is we use sort of, as much as possible, we use off-the-shelf sensors. So the best wind sensors we've been able to find, they sort of flatten out. So somewhere's around 50 knots. This was just random noise. We believe in this region here, the actual reading would have been up there. But nobody makes sensors for high-speed wind that are marine capable. Why? No ship will survive high winds. You know, if you've got 50-knot winds, I don't care what kind of ship you got, it's dead. And so there is no market for instruments that you fit on something that's going to be dead anyway. So we try to be, you know, the eyes underneath hurricanes. And we had, so in the recent hurricane that went over the Hawaiian Islands just a month or two ago, we had 13 Wavegliders out underneath that. One of them, well, only one of them had a camera, and unfortunately it was sort of on the lee side. When the hurricane came over, it was night. So we got some interesting footage leading into it, but you know, as the hurricane came over, it would have been a lot more fun to have cameras on the other side. Yeah?
So you said that this is the only kind of sensor that you have that can be looking at the belly of the hurricane, as
well,
as satellites that are looking from above.
Yeah, well, we're kind of the only sensor platform, but people put a lot of other sensors besides wind speed on there.
Okay. Well, so I'm just wondering, like, do you need to be underneath the hurricane in order to see it, or can you see it from satellites just as well? Or is it like...
Well, from a satellite, you can see the top of the clouds.
Okay, so you can't tell that it's a hurricane.
Well, you can tell that the wind speed is high at the top of the clouds. If you're lucky, you can see inside the funnel, and they can do sort of Doppler measurements on the inside of the funnel. But a lot of what matters in the dynamics of a hurricane is like how much energy there is in the water in terms of heat. So you need to be able to measure the temperature of the water, and they can do kind of gross measurements, kind of, from satellites, but it's not nearly the same as having an actual sensor in the water. And as soon as you're covered by clouds, you can't tell anything. And kind of the definition of a hurricane includes a lot of clouds. So, you know, a lot of the unpredictable nature of hurricanes is they can only get this kind of superficial data. They can't really tell. They can't get the core data for the energy equations for what drives it, because it's all driven by the heat in the water. And salt water. Salt water is like extraordinarily corrosive. Doing electronics anywhere around salt water is entertaining. And you know, we've had terrific issues with there's this phenomenon called crevice corrosion that even you think of metals as like stainless steel as being really good in salt water. But as soon as you have two pieces of stainless steel that abut each other, you get this phenomenon called crevice corrosion, or if you have like a small crack in it, it can eat away. And if your steel is if you're able to service this thing every few months, the steel is okay. Or if leaks that come in, all ships have like bilges and bilge pumps because they pump the water out, but when it's electronics on the inside instead of just like open space that you can pump the water out of, it's different. So we use a lot of titanium, a lot of machined titanium. The hull, I don't really know what the hull is made of. It is some exotic relative of fiberglass. We use some carbon fiber. We use carbon fiber for the masts, but you can't use carbon fiber for a hull because carbon fiber is conductive, and if you attach metals to a conductor in salt water, you've made a battery. And whatever metal it is, it just sort of plates away, and you've made a fish shiny. Not terribly useful. We do actually have to deal with sharks. We don't have too many shark incidents. They're usually not interested in us. One of the weird things that happens with us is that if we're within 10 or 15 miles of the shore, little fish find us. And because we cast a shadow, we look like we're a safe place to be. And if you put one of our Wavegliders in the water and then you come back a week later, it'll have a ball of little fish. You come back like a week later and it'll have a ball of like bigger fish. And so I end up going out to work on these things a lot. I do a lot of software debugging at sea, which is like a really different, any kind of software debugging that involves putting on a snorkeling mask, that's a good software job for me. But we always have like divers that come along because they're supposed to be looking where I'm not looking. Because they're always interesting things, and half the time they end up bringing home lunch, which is always tasty. So this is one that's been mauled by a rather large shark. Mostly he just scratched the paint, more paint scratching. We sort of figured, given with the placement of the scratches, his mouth must have been about 3 feet wide. And really all he ever did was scratch the paint, except for in one place there was a cable that went over a little joint knuckle, and he nicked the cable right there, and that was the cable that connected down to the rudder. So we lost control of the rudder, and it was just floating. Fortunately, it was a couple hundred miles east of Maui. He was on his way from San Francisco to Maui. And so we just let him sort of drift in the current a bit more, and then we went out in the boat and got him. But most of the critters that we get are less scary. These are gooseneck barnacles. Mostly when people make robots, they don't think very hard about what kind of paint you put on them. We have to think really hard about the paint that we put on things, because the kind of paint affects what can grow on it. So the longer you want to be out at sea, the more hazardous the paint ends up being, and you end up with these epoxy paints that are embedded with copper is the best one. This is a paint that's got a lot of chlorine embedded in it, so it really slows down the growth. This is a Waveglider that had been in the water about 4 months. If you just had sort of like a naked hull, it would just be totally covered in barnacles, and they would be much bigger than this. So what do you do with them? It's kind of like a weather buoy that installs itself. So these two actually have essentially the same instruments, even though the one looks a lot bigger. The deep ocean buoys are actually really expensive. Not because the buoy itself is expensive, but the boat to go out and install one or do a repair job on them is about $150,000 a day. So to go out to the middle of the Atlantic to fix a broken buoy is a couple $1 million. So you want to replace a cracked solar cell or something, it's a couple $1 million. Our little guys, you just sort of throw them into the ocean in Miami, and they swim out to the middle of the Atlantic, and every now and then you have them swim back and you scrub the barnacles off and they go out again. Hello, Phil. We do a lot of stuff like pollution monitoring. You can get like chemical sensors that go on them, and we'll circle your oil well to do measurements for pollution. We do a lot of global warming studies. We had 9 Wavegliders up in the Arctic this year. I'm not sure what the numbers are going to be like from those. It was 4 missions. I'm not sure who they all were for, but a couple of years ago we did the largest ever survey of ocean temperatures in the Arctic, and the numbers were deeply scary. Be afraid. We do a lot of work with sort of underwater communication. So there are a lot of sensors that go on the sea floor. So a really popular sort of sensor is a tsunami sensor. So for a tsunami, you'd think you'd put something on the surface that would just sort of bob up and down with the tsunami. The problem is that a tsunami is in the middle of the ocean is only like an extra few meters in height. They're very, very broad, but they're shallow. So it's, given all the other noise from all the other waves, it's really hard at the surface to distinguish a tsunami. But there's so much mass involved in a tsunami that what you do is you put a gravitometer on the seafloor, and you can actually measure the distortion of the Earth's gravitational field because of this wave that goes over. And the problem with putting a sensor like that on the seafloor is, how do you talk to it? Radio doesn't go through water at all. It's 1,000 miles offshore. Standard practice is to just like roll out 1,000 miles worth of wire. So the vast majority of the tsunami sensors out there are connected by wires that are broken. And so but you can have acoustic modems that work for, so an acoustic modem is good for, in the water, good for like 5 miles or so. So what you do is you have one of our little guys, they just sit there doing donuts for months, talking on an acoustic modem down to the gravitometer on the sea floor, and then sending messages via Iridium that something was sensed. What the Japanese do is they actually have ships with people out there at $150,000 a day-ish. And that's just crazy expensive, and they only manage to do a few. But they care a lot. But we can, that ADCP thing that's for measuring current flow, you can also use it to count fish. So people use it in the fisheries business to, measure where there are schools of fish and public transport. We get blue-footed goonies, and one of the things that's entertaining that we have a few photos of is of killer whales in the area around along the California coast, around the mouth of San Francisco Bay. There are a lot of killer whales and there are a lot of seals, and the seals try to stay away, and if they're being chased, they try to find someplace safe, and occasionally you'll get a seal that will like come flying out of the ocean and land on top of our solar cells, and they'll just sort of park and they'll sit there as this killer whale goes around them, and it's like and we've had some boats actually get pictures of that happen, and it's like okay. So what have I been working on? I've been working on the current generation, which has a lot more power and a lot better hydrodynamics and whatever. And one of the things we're really working on is collaborating fleets of these things with much more sophisticated navigation and power management and the rest of it. And one of the things that makes these things really different is that they have to be truly autonomous and truly robust, right? So if things fail, there isn't like, a lab technician on the other side of the room to walk over and jiggle something, right? If something is going to get jiggled, the software has to do that. So we have, as much redundancy as we can get, all kinds of failover strategies, all kinds of things that we try to do to sort of correct problems and do it with as little involvement from the shore, because often there is no connection to the shore. We have to be able to do things like dodge ships on our own. So in this generation, what we did a kind of a dumb thing, which is we sort of kept the basic concept, and we just redesigned everything from the ground up. The guts of the electronics look oddly enough like a cell phone. Right? Kind of everything looks like a cell phone these days, because the the volume parts you can get are ARM processors, and we do this all using Java SE embedded, and all of this wiring, all these blue boards, those are parts of the power supply. And we have the world's most ungodly power supply, because everything that gets power, we individually meter and monitor and isolate. If we get a saltwater intrusion into a cable, we need to not be affected by it. We need to be able to tell that it happened. We need to be able to cut that thing off. We have to measure everything. And if you pull, this is a hull that's got the long duration copper paint on it, rather than that shiny yellow paint. And so if you look at the hull, it's kind of like a data center rack on its side, and the boxes that we put in are all watertight, and they all have these ungodly cables, and all these connectors are saltwater mateable connectors, just crazy cabling. All of these parts are expensive. It's just crazy. So we have a network architecture that these things fit into that's relatively conventional. Namely, we've got a data source on the side that's the Wavegliders. It's talking through usually a satellite. Sometimes it's a cell phone, down to a satellite ground station, and then we've got this redundant network of sort of data repositories that feed a combination of web applications and desktop applications. So the piece of software I've been working on is this thing that we call Regulus. It's the command and control software that runs on the Waveglider, and it has sort of a half of it that runs on the shore side. It's all running in Java. It runs on Timesys Linux. The JVM that we've been using has been just freakishly solid. And we use, one of the nice things about writing Java programs is that there's this huge collection of libraries for the strangest things, from libraries for doing mapping, like storing like a detailed outline of North America and reasoning about its shape, to libraries to do given the lat, long, and time, work through the world magnetic model and compute the declination, or astronomy libraries. I love astronomy libraries. It's nice to know what the sun hitting the solar cells ought to be, and you need astronomy to figure that out. But when you look at the code in a beast like this, it's sort of like 10% sexy, interesting stuff, and 90% of it is just staying alive. It's doing things like managing GPSs. You can't get a chip these days without getting a GPS receiver for free. So we never have fewer than 3 GPS receivers. And one of the things that just keeps shocking me is just how flaky GPS receivers are. They're the single least reliable part of our system. The second most unreliable piece is compasses. We had an entertaining issue this summer where we had all these Wavegliders that were being sent up to the Arctic. The electrical engineers all said, "Oh, no problem. Those compasses, they'll all work up in the Arctic. They're not too close to the North Magnetic Pole." And they all got dumped in the water across the span of a couple thousand miles, and all of the compasses failed. And so it's killer robots with laser cannons totally out of control. And so I had to spend 3 days not sleeping, figuring out how to fake the existence of a compass from GPS. And then one of the nice things you can do with Java is injecting code. So we were able to patch these robots on the fly in the ocean, and that was entertaining. So the guts of Regulus is a fairly normal sort of system that's made up of a selection of services. At the core of it is sort of life cycle management. The system behaves as though it's always booting. You know, in a normal operating system, you go through a boot up phase and then you're running. Because stuff is always failing for us and then it's coming back, effectively the system is always booting. There's a fairly complex mechanism for managing the interdependencies between components. You know, because there are, for instance, components of the system that need to know the location. And so they get started up after the location services start up, and the location service starts up after at least one GPS receiver starts up. And there's this dependency graph that we generate that manages a lot of the fault recovery and fault recognition and the sequencing of operations. There's a general mechanism for doing sort of election of a sort of a winner if you've got redundant sets of things like multiple compasses, multiple sources of thrust, multiple sources of power, multiple GPSs. You have to figure out which one to believe. We don't do. I keep having this debate with myself as to whether to go like full Byzantine on this, because some of the there are things that fail and you know that they failed, but then there are things which fail but they're just really just lying to you, and understanding the difference between failure and a lie can be difficult, and not managing that as well as we should. Right now it's just kind of like a simple voting mechanism, and sometimes the voting mechanism, you know, if all the GPSs are misbehaving but there's one good one, usually the one good one is the one you don't believe, and that's not a very good idea. It's highly concurrent. You know, I love threads. I love garbage collection. Services tend to be fairly simple. You can declare dependencies on things in a fairly straightforward way. You can subscribe to messages from things. This is a service that just prints a message whenever you cross the equator. I know everybody's system has one of these, right? But it's you know, it's fairly straightforward and has all kinds of like failure recovery in it, and there are a bunch of standard systems that we have for things like service management and device management. Some that might seem a little odd, like we've got a situation awareness system that is looking at all the sources of data about things around us. So things like RF beacons from ships, acoustic signals from their propellers, mapping. Then there's another service that represents kind of the mission we're on. What are we trying to do? Sometimes the mission is really, really simple, namely go to that point, go in circles for 5 months and then come home. Sometimes it's more complicated than that. And sort of the situation and the mission come together as things that feed into the navigation. And then we manage things like all the power and monitoring and crap like that. So one of the more interesting features of this thing is around autonomous navigation. We use sort of a potential field navigator, but because the area is so large, if you do just sort of a classic kind of potential field, you have like numerical stability issues because you tend to be fairly far out, and so things become numerically unstable. So it's actually the sort of the first derivative. It's the force vectors. So all the sources into the planning system, they emit force vectors, and then they're merged as force vectors rather than as height fields in a potential field. So here's a simulation from a year or so ago of vessels doing sort of a picket fence. You know, say you were trying to protect a sanctuary, or you were trying to do drug interdiction. You want to put a picket fence of monitors on the U.S.-Mexico border. So there are these are traces of Wavegliders, and they're all given exactly the same mission, right? So the mission says, here's a line, stick on it, and at the same time, stay far away from your neighbors. So 4 of them get dropped in the water, and they burst to stay away from each other, and then they start going towards the line. And then the 5th one gets dropped in, and you see when the 5th one gets dropped in, it goes to the line, and these 2 sort of move out of the way. And that's sort of a behavior that just sort of emerges from a really simple plan. And it's one of the nice things about this style of planning is it's highly adaptive to variation. So if you do exactly the same mission, only you drop the Wavegliders into the ocean at a different place, they approach the line differently, they sort out differently, and if you here when the 5th one gets added, it's added over there, and it swims towards the end, and all of the others just sort of shuffle down. You see how they all shuffle down there. And they do a really nice job of optimally getting to where they need to be and keeping the spacing on the line. And so you can get some pretty sophisticated behaviors out of really simple rules. And so here's the same one again, only there's another thing that comes through, and this is a ship that acts as a collider. And you see here, it's the collider pushes this guy out of the way. So this red one gets out of the way to avoid the ship. But you notice that this yellow guy here, he moved over, and this guy here moved over because they're also trying to maintain the spacing. So to avoid leaving a gap, a really long gap here, this guy moves over, and it just sort of all comes out in the wash really smoothly.
Those robots know where the endpoints of that line are?
Yeah, that was part of their mission plan, right? They're told stay along this line. So here's this is a screenshot from a completely different mission planning system. Those were simulations. This one is real. So this black line here, we have there's a chunk of ocean off the west coast of Hawaii that we have it's called a posted notice to mariners. The notice basically says, experimental killer robots with giant laser cannons at loose, stay out. And mostly people stay out. Fishermen stay away and tugboat captains stay away. But the Navy doesn't care. The Navy doesn't pay any attention. So when we're not doing anything with our experimental guys and we're just doing it like endurance testing or something, we tend to have them just go in boxes. They'll just go around in squares. And so we had these 2 guys going around these boxes. And the ship that was some Navy SEALs doing some diving exercises they just kind of like moseyed on into our area. And you can see how this one chose to flee, and this one chose to just kind of keep your distance. One of the things that I really like about these sort of potential field planners is you can do blending of strategies. So we actually have multiple strategies for avoidance. Right? We've got sort of stand your distance, loiter, and flee. And they can actually do sort of blended versions of them. So it will start fleeing, and then it will sort of arc around and just nicely go around the ship. And this one was just so perfect because it was this was a real ship full of real Navy SEALs, and we just stayed away and let them be. This one, I know it looks like some ugly piece of art, but this was given a mission plan that is essentially choose a random point, go there, when you get there, choose another random point. One of these vehicles will just, that's just like a standard mission. It's like, here's a chunk of ocean, go randomly wander. You put multiple Wavegliders in the same chunk of ocean and tell them to wander. They keep out of each other's way. So the blue wave, so the blue Waveglider didn't have a way to transmit its position. It didn't have an AIS transmitter. So the red guy could never tell where the blue guy was. So the blue guy was doing all of the evading. So the red guy, he's just going zing, 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 back and forth. I let these guys just go for like days and days. And the blue guy was just like getting out of the way and, oh, excuse me, getting out of the way. Because lots of folks were they had seen several examples of collisions that were avoided. And we had some folks that just wanted to believe that it actually worked, something that was not a simulation, that was like actually out in the ocean. So I just put two of them in the same piece of ocean and set them up on a course that would cause just an ungodly number of collisions. And with a plate of spaghetti, but no collisions. So that worked really well. So, one of the things for me of playing this out over the last couple of years has been that the autonomy, the control algorithms, they're really easy. The place where we have a hard time is with the sensors. How do you sense colliders? The sensors are really tough. Mostly what we use, other than my unbelievable inability to spell, are these RF. So ships beyond a certain size or beyond a certain distance from the shore are required to have RF transponders. It's a standard called AIS. And we use AIS for everything. And mostly AIS, particularly in the deep ocean, is a great way. It works really, really well for everybody except the Navy. We lost one a few months ago because the Navy was doing exercises in an unannounced place that intersected our area, and for part of their exercises they went dark. So they turned off everything, and then all of a sudden our guys couldn't sense them. And one of our guys got eaten by the propeller of a rather large vessel. So that was not pleasant. We were unhappy. We've been doing a lot of stuff with acoustics, and I think we're almost ready to use them for real. Been dabbling with various sorts of sonar. Cameras aren't nearly as useful as you'd like them to be because there are waves. Yeah.
So how would you tackle a problem like invisible ships, like marine, like that?
Well, they pretty much all have engines on them. And engines have a very characteristic acoustic profile, right? So you just have you just listen. You do an FFT. If you've got a peak somewhere that's kind of low, then it's almost certainly a ship. If it's really low, then it's it's like the larger the ship is, the lower the frequency. But you can definitely, it is by a wide margin the most reliable way to detect a ship is by listening to the engine noise. And oddly enough, even sailboats of any size have to have generators on them all the time. You can't run a winch without an electric generator. And then that leaves small sailboats, and if one of our guys collides with a small sailboat, it just sort of bounces off. We haven't had any trouble with that. We've bounced off of lots of sailboats. But if we get pulled into the propeller of an aircraft carrier, we're not going to bounce off. We have a really, really great audio unfortunately, we were not allowed to play it, but because there was like insurance liability issues. There was the pilot of a large ship in the Gulf of Mexico had his AIS transmitter turned off because he wasn't behaving correctly, and we collided with him and got eaten by his screws. But we had like an extremely expensive hydrophone array that we were pulling and recording it onto a flash drive. And this was sort of in the middle of the Gulf of Mexico, which is like packed with oil rigs and stuff. And we were doing sort of some kind of a pollution monitoring thing around a rig. So it got eaten, and some guys went out and they found the wreckage, and in amongst the wreckage was the flash card. So we have this great audio of this thing being eaten by the screws of this giant ship, and it starts with this sort of which is just like the screw noise, and then the screw noise gets closer and louder, and you need a really good stereo system to listen to it because it's really low frequency. It's like it's all bass, right? And then it gets eaten, and you go, and then it's silent. It's a lot of fun. So we did a bunch of missions in the Arctic. We had three. This is actually 3 Wavegliders over here by Greenland. 2 of them were really close together. Then we had some in the Beaufort Sea over here, and a bunch over in the Chukchi Sea. And other than issues with the North Magnetic Pole, which is kind of a little too close, and ice, they worked really well up there. We got some great pictures of icebergs that I would love to be able to show, but we.
Your video connectors are those. Yeah, one of the pins.
It looks blue.
Yeah, on your screen it's white.
Oh, right.
Your cable's a little loose.
Is that better? All right, a little better. This is all pack ice up here that we were trying to thread through. We need better sensors for pack ice. One of these 2, I think it was this one right here, the 016. He got crushed, but otherwise they all made it back. Fault management, that's a big deal for us. One of the things that people find really annoying about Java is that there are all these mechanisms in there for handling faults. So things like the exception mechanism, opaque pointers, the way that you can't lie about memory integrity, and you can't turn checking off. Those turn out to be what saves your bacon in building reliable systems. Gives you a really good way of isolating failing components, so that when software breaks, you can just sort of isolate it and either retry it or stop it or whatever. When we have bugs and the vessel is out in the ocean, it can't just core dump and say done. It's got to carry on, right? The sort of standard practice for in most of the software world is you get a memory exception, you die. No, got to figure out how to carry on, and a lot of stuff in the Java memory model is exactly for that. And people use that all the time in things like app servers. If you look at Java EE, a lot of the hairy bits of Java EE are about sort of managing faults in the midst of doing very high transaction loads, and dealing with this through redundancy and failover. And we do lots of retries of software failures and hardware failures, and dicking around with power supplies. I mean, half the reason that those power supplies are that complicated is so that we can power cycle individual components, try to figure out what piece is failing. So if we've got like a saltwater intrusion into the wire into the motor, we can cut off the motor without cutting off the rudder. And that makes everything, and of course instruments lie, everything lies. Communications, communications are actually fairly interesting. We've got this communication system where you emit messages, and they have sort of three measures with them. There's priority, which is sort of how important it is that it get to where it's going quickly. So something that's being used for navigation will have a high priority. Something that's just like scientific measurements of salinity, it'll have a really low priority because you really don't care, if the salinity measurement gets to where it's supposed to go kind of late, but the navigation stuff gets through first. But on the other hand, the salinity measurements are why you're out there in the beginning. So that data is really important. So if you're end up queuing the data on disk, stuff of low importance you delete first. And so something like a science measurement would have low priority but high importance, and something that's useful for navigation will have high priority but low importance. Because if you've got some navigation issue from like a week ago, you really don't care about the evidence of that if you've survived the last week. And then sort of coupled with, it kind of falls out of importance, but we have it as a separate parameter, which is how much are you willing to pay to get this to shore? Because all of our different channels have different costs, and often the costs are just money. And the different devices have different latencies, different bandwidths, different costs, and particularly anything having to do with a satellite link. So we typically deal with 3 satellite links. Always we've got Iridium SBD. Sometimes there's a satellite standard called BGAN, which is what most people do, like streaming audio with. And then there's another Iridium thing called SBDIX. And they all have different costs and different latencies, and they survive different environmental conditions differently. So something like a BGAN, and BGAN is the one that requires a dish about this big, and if you mount one of these on our guys, it has to be in a dome, and then they have these servo gimbals that point it at the satellite. But if we're rocking a lot, we can't lock to the satellite. So if we're in a storm, BGAN is completely useless, whereas Iridium SBD, which has an omnidirectional antenna, that one keeps working. SBD works everywhere. It's crazy how well SBD works. It's just $1 a kilobyte and 1/3 of a kilobyte a minute. Security, God, I could spend an hour talking about security issues. If only because some of our customers are scary people. And actually, often the people who care most about security are like the oil companies, right? The oil companies really don't want their competitors to know, where they are, where they're looking. So if Shell Oil is doing a seep analysis over a piece of ocean, they do not want British Petroleum to know that. And these guys get really cutthroat about it. And so they get very, very paranoid. And so like I would love to show you some pictures of icebergs. But because that was done for an oil company, they said no. Write once, run anywhere. One of the interesting things about Java code is you can run it everywhere. And so we tend to run the guts of a Waveglider on things other than Wavegliders. And in particular, we run it inside simulators, we run it inside test harnesses. And one of the weirdest things I do is I actually run the guts of the Waveglider inside the Waveglider. So, and I do that kind of as a simulator. So if we're I said we use this sort of potential field planner, but sometimes you get points in the plan where you could go this way or you could go that way. Then what we can do is run a simulation, right? If I choose turn left, then if I choose right, then run the simulation. And then you run the simulations until they end, or until you've got some idea of which direction was the best way to do it. And I do that by running exactly the same navigation code inside a simulation, inside the real thing. Yep.
Sorry to interrupt, but just to let you know, there's another SCS event at 4:30.
Yeah. I'm rambling here. Anyway, that's me. That's debugging. So I want to do a quick demo. So this is our engineering centers in the Kona coast. So this is actually live telemetry. So if I zoom in on this guy here, if I zoom in enough, you can see him. We've just got him sort of chugging along. And if I say view, I'll bring up his deck camera. Oh, come on. There we go. All right, so. Oh, come on! One of the problems we have is that the cell modems on these things are really crappy. I hate VLC. I hate VLC. It won't even quit. Fucking A. All right, let's. Yeah, so he's there.
So what's the scale, like from that point to the land?
So his box here is 700 meters across. These are our test vehicles, and the ones that we go out and play with a lot, we keep them close to shore. So he's like 6 kilometers from the shore, 5 something.
Because if you look in the video, it looks like that's land. That's pretty close.
Yeah, well, that's there's an island there.
But it doesn't look like it's 6 kilometers away. It looks like it's like 500 feet away or something.
Yeah, I mean, there's a decent lens on this thing. The cameras on these things are kind of funky because they're cameras that have to work inside hurricanes. So it's not a GoPro.
Oh, yeah, I'm not disputing. Sorry.
So you were lamenting the fact that you could only see one side of the hurricane that went through.
Yeah.
Not putting like a pan on the camera is just for simplicity's sake?
Yeah, we've played around with various kinds of pan mechanisms, and
I mean, that would seem to be a priori so valuable that it'd be worth.
Oh well, no, the way you pan. Let me get this out of the way. The way that you pan. Oh, don't try to talk. Nope. The way you pan is you tell it to go, is you just drive the vehicle around. So that one of the camera commands is go take a picture of that. And you give it a lat long of that, and it sort of steers towards it. So I just gave this guy a little mission. So he's now going to turn south. And if you watch through the camera, it's now panning effectively. But it's, because we can steer the boat, you get panning for free with no mechanics, right? And actually, if those clouds were not there, there's a lot of telescopes right up there. That's Mauna Kea, where there's all these giant telescopes. So you can see here, he's now turned south, and he's actually pointed at a bunch of golf courses. Now he's sort of pointed out to more out to sea. But he's sort of starting to head down, and he's fighting some current, so he's pointing in an odd sort of direction. But if I now tell him to go, navigation, come on, stupid menus. Yeah, there's a lot of things you can tell these things to do.
So we as people can do the same thing. You know, we can look without turning our heads by walking in a direction.
Right.
But nature has blessed us with the ability to look in directions that we aren't traveling.
Right.
And it's a really good thing to do.
Well, absolutely, and every mechanical mechanism that we've
I
tried.
understand that, but that seems like kind of, in my mind, that trade-off seems to be highly in favor of adding that one extra.
Absolutely, and we continue to try to find one that does not fail.
Okay, so that was the question, why not do it? You say you are doing it, it's just...
We have not yet found one that does not fail.
Okay.
Right. I mean, trying to mechanically have a mechanism that handles so you can put them in like a bubble, and then you have to figure out how to keep the glass clear, or you articulate the whole thing, and then you have to have a joint that's exposed to the weather. And then you have to deal with the fact that 60-foot waves, period of 60 seconds being slammed at you, gigantic forces on this joint, and trying to sort of mechanically engineer joints that will deal with that, because these things, if you're in a hurricane, one of the things that happens is this thing gets thrown ass over tea kettle out of the waves, and it will come back, tumble down and land. We do lots of simulations of how these things like tumble down and land. That umbilical that connects the float and the sub is probably the single most exotic piece of engineering on the whole thing, because the cable has to handle unbelievable shock loads. Normally, shock load's not very much, but in the midst of a serious storm, the shock loads are really, really high. But it's also got conductors in it. So how do you make conductors that can be in a cable that is both flexing very rapidly and has really dramatic shock loads? So there are the wire that we buy costs something like $20 a foot, and it's all these like little micro fibers that sort of slide amongst each other, and it's just crazy stuff.
So this is a follow-up to Dean's point. Why can't you put a fisheye lens on the front of the camera? It's a solid piece. And then if your camera's high resolution enough, you can still have the software effect of the...
Yeah, and we'll probably end up doing that. We're still kind of shopping for sensors, finding sensors that really you can find lots of like big sensors in like good cameras, but you can't actually buy the sensor. You could take a Canon EOS and put it in there, or you could take a hammer and take a Canon EOS apart to get the sensor out, but you'll never figure out how it electrically works. A lot of the trouble in building these things is you just can't even get the parts, because like you can't buy an ARM chip, right? You can only buy ARM chips mounted on boards. So if you want to design your own board, you have to buy a board and then take that board and mount it on your board. Because if you go to somebody like NVIDIA and say, I would like to buy an ARM chip, they'll just laugh at you. They'll say, well, our volume, you can buy 10,000 of them. That's like the smallest number they will sell you. And if you're willing to throw away 9,999 chips just to get one, you're okay. But it's sort of a weird world. Yep.
You were talking about pollution pollution monitoring, I'm wondering if you guys are looking into like actually pollution cleanup at all, like having some kind of device that could actually filter the surface of the water, maybe if there's oil floating on it, or maybe like if you had fleets of vehicles that could be heterogeneous.
We would love to get the purchase order to do that. We would love to do that. It would take millions of these guys to make a dent in it. I mean, the ocean's an unspeakably large place.
Like a heterogeneous fleet, and maybe you could have a larger thing that isn't as smart, but you can
Right.
use the smaller guys to tell the larger
Right.
guy to go.
And we would love to build that. The problem is we've never found anybody who would be willing to pay for it. You know, and as good as that would be for the planet, it would be real expensive. And if, you know, if the UN was to drop $1 billion on us, we would do that in a heartbeat. But, yep.
What's the uptime on the locomotion? Because you need waves going up and down to be able to get thrust, right?
Yeah, so we get useful thrust out of waves of at least ½ an inch. And believe it or not, in the Gulf of Mexico in the middle of summer, ½ an inch is about what you get.
Any designs that work on, say, a freshwater lake where there may not be waves or anything like that?
On a freshwater lake like the Great Lakes, or oddly enough, we've done a lot of work in Loch Ness. Somebody gave us money to go chug back and forth in Loch Ness. Works great. Works great. We actually don't need much in the way of waves to get a significant amount of thrust. They work well in lakes, but you know, most of the work that the problem with lakes is the lakes are usually small enough that they're economical to do tests on them in boats with people on them, and where the economics become really overwhelming is deep ocean. And so like in the Great Lakes, or something that's like really boring and monotonous, like if you want to go from end to end of Loch Ness, doing water chemistry samples over and over and over again, it would, you know, the crew of the boat to do that would go insane. Whereas our little guys are happy to spend month after month just going up and down and up and down and up. They don't care. Yeah. So lakes, so long as they've got you know, waves of kind of like that, and we'll get a decent speed. Yep.
So in the system diagram you showed at the beginning of your talk, there was a third component labeled toefish. What is that?
So often people want instruments that are really sort of isolated from as much motion as possible and as acoustically isolated as possible. So if you want a modem to talk to a seafloor sensor, and you want to be able to talk to a modem over a long distance, like if the water depth around the Big Island tends to be around 10 to 15,000 feet. I mean, it's like a cliff at the edge of the islands there. And through a lot of the deep ocean where people would want to put gravitometers, they're kind of at the edge of where modems work. And so if you can keep the modem as sort of acoustically quiet as possible, and so we kind of go up and down. And by having this toefish, you've got this thing that's below the turbulent layer of the ocean, is down where the ocean is really calm. It's just got, and the toefish had like this sort of curvy thing going up, and what we do is we take the cable and we have weights and floats and weights and floats, and by doing that you get a sort of accordion pleat in the cable, such that if we sort of jerk forward, the accordion pleat just sort of stretches out a little bit, so that we keep the toefish going at a very constant rate. And so then that gives you a fairly acoustically quiet environment, so that things like modems and hydrophones and that, they work better. The seismic guys like to do that as well. and all kinds of chemical sensors work better if the water flow over the sensor is very sort of laminar, is very smooth. So we've managed to, so the toe bodies are really good for things that are sensitive to the smoothness of the flow around them.
So you have time for one more question?
Way at the back there.
Yeah, it's too much power to use HF radio, like 20-meter band, something like that. Just with a small antenna size.
Yeah, I mean, we could, we could do that in short bursts. I mean, we instantaneously have actually gobs of power. We have, because we have big batteries. The problem with things like HF is that it tends to be somewhat erratic, depends on like the ionosphere and such. And so if you try to deterministically reach a point with HF radio, it's somewhat random. We keep trying radios. I mean, we've got a scrap room filled with radios, and we found a few that work reasonably well. So we've found a couple that can give us like 20-ish miles. But to get sort of 20-ish miles, that's beyond, you know, because we're close to the surface of the Earth, and so the curvature of the Earth cuts out a whole lot. So you've got to have some kind of bouncing, you know, so you can, you know, you can bounce off the ionosphere if you're trying to go a really long way, but there's this weird phenomenon called evaporative ducting, where, you know, body of water, it's evaporating, and the moisture acts as a lens for radio waves, so you can get a certain amount of, so if your transmitter is within about a meter of the surface of the ocean, and the waves aren't too big, it will sort of bounce through this duct, and you can get like 20-ish miles. So for some applications, that's worked okay. You know, one of the things that's difficult for us is it doesn't matter if we've managed to get it to work once or twice. It has to be like reliable. It has to work over and over and over again. We've got to be able to know that we can depend on something.
And a marine radar, you can't get up high enough. Like you need it too high of a mast.
Yeah, we've tried. Yeah, for things like marine radar, you have to get somewhat higher than we can go. You also end up with a big mass on the end of a moment arm, so it tends to want to flop over. And we've played around with a number of those. There are actually some customers that do that. They're kind of hokey and they don't survive much weather. And most of those radars, they don't work well if the thing that they're mounted on is swaying a lot. And because we're so coupled to the waves, you know, we sort of sway back and forth a lot in the waves, and so that definitely causes us some problems. But by coupling with the waves, we get both energy and durability. So, thank you. I guess we're.